Welcome back, everyone. This slide is second out of 3 and we'll cover alloy steels and heat treatments. Page 3, alloy steels are specified by what has been added to it. The amount of alloying elements in low alloy steels is less than 5%. Some common additives are aluminum, which is used as a deoxidizer, chromium, which will increase corrosion resistance, molybdenum increases hardness and is used for strengthening steels. Tungsten is added in small quantities due to extreme hardness. Tungsten retains hardness at very high temperatures, even when it's red hot. This is why it is used as the electrode for TIG welding. Page 6 shows how the American Iron and Steel Institute designates alloyed steels. One thing to keep in mind when welding low alloy steels is to use low hydrogen electrodes at their proper holding temperatures. Here's an example of how plain carbon steel with 0.4% carbon content is designated. Page 9 moves on to high strength low alloy steels. This material combines strength and ductility, which means it can be formed without becoming fatigued and breaking. The picture you see is AR steel plate. AR stands for abrasion resistance. It can be detected easily by sharp square corners compared to mild steel that has rounded corners. You guys have probably used this stuff already. It's used in metal to metal situations like conveyors and whatnot. Preheat is a pretty good factor with this. The difference between mild steel is the yield strength. Yield strength for AR plate is 90,000. Yield strength for low carbon steel plate is 30,000 psi. Page 10, stainless steel is a combination of iron, carbon, and chromium. The chromium content must be at least 10% to be considered a stainless steel. This alloy is classified by a 3-digit number. The most common grade is the 300 series, which is known as austenitic. Stainless starts with combining chromium and carbon, which provides hardness. The addition of nickel improves corrosion resistance. The 3 main stainless types are austenitic, martensitic, and ferritic. Austenitic is commonly known as the 300 series and contains 18% chromium and 8% nickel. The grain structure is face center cubic and is generally non-magnetic. Martensitic stainlesses are mostly the 500 series. It has a very hard grain structure and is crack sensitive after welding. Ferritic stainless is heat sensitive because of the very high chromium content. Some are up to 27%. When welding ferritic stainless steels, small electrodes help to keep the heat down. Duplex stainless consists of 2 structures, the austenitic and ferritic structures. The standard grade duplex 2205 is most common and is showing up more and more in the pulp mill and oil and gas industries. Once you guys get through your practical in the shop, we'll be able to play around with some 2205. Page 15, the main problem associated with 300 series stainless is carbide precipitation and distortion. Sugaring is another common problem, but is mostly from lack of setup by the welder. Carbide precipitation happens when the chrome and carbon are drawn out of the material and react with the atmosphere. It's often from too much heat or welding too slow. Since austenitic stainless has poor thermal conductivity, it tends to distort easily. Some stabilizing elements that are used to prevent chromium loss are titanium and columbium, which are shown here. The 321 and 347 are good things to jot down because that is on your test. Some considerations to think about when preparing a stainless joint is reserve wire wheels and grinding discs for stainless. Don't use cellulose coated electrodes because they do contain moisture and it'll cause cracking. Clean in between weld passes to remove oxides. Interpass oxides will slow you down, especially when you're TIG welding. Using a higher amount of sealing gas flow will help cover the weld to prevent carbide precipitation. And always purge the backside of a weld joint to prevent sugaring of the root pass. I'll post this how it's made video link on your Moodle if you'd like to check out how stainless steel is made. The next 4 slides are a review, and they show the need to know goods. You can pause this as you need to. On page 22, we can look at heat treatments for steel. A full anneal is when steel is heated 10 degrees above the upper critical temperature and then cooled slowly in a furnace. The upper critical temperature for carbon steel is 910 degrees Celsius, which is just below the transformation to ferrite. The purpose of annealing is refining the grain structure to make it softer for machining purposes. Normalizing and annealing are quite similar, but the main difference is that normalizing is cooled in air naturally. Cooling in air speeds up the cooling rate and makes the steel harder. Both normalizing and annealing soften and improve machining of steels. Page 23, stress relief annealing uses a lower heat input than annealing. And process annealing is used to remove residual stresses. The main 2 for you guys to be concerned with are normalizing and annealing, and the way that they are cooled. All these treatments induce ductility, soften the metal, and improve working properties. Quench hardening is when steel is heated up to 1400 degrees Celsius and then rapidly cooled in water or oil. This produces the microstructure martensite, which is hardened and prone to cracking. To reduce cracking from quenching, tempering can be done. Tempering will relieve internal stresses and reduce brittleness. These steps are used in making chisels. Page 26 in your book shows steps for hardening and tempering a chisel. Page 26, last part here. Peening is done to balance the shrinkage of welds as they cool, which prevents cracking and relieves internal stresses. A ball peen or air hammer can be used and is quite commonly done when welding cast iron. The next 3 pages are summaries. As I said before, you can pause it as you need to. There will be flashcards posted to Moodle for this section and the other sections.